Ladies and gentlemen, class recording has started. So, yesterday, well, Tuesday, I guess, we started talking about this idea of orbital diagrams. And like the first title says, it's about orbital filling. When we drew this picture, not this picture, but this picture, right? Yeah, actually, this picture, okay? Right? All of these spaces that we drew, we said were orbitals. Orbitals are areas of higher electron probability based on the previous location of electrons. Schrodinger works out his wave equation, and it gives us probability. But are all of these orbitals an equal do all of these orbitals have an equal probability of us finding electrons in them? No. Some have higher probabilities than others. What is the one determining factor that really tells us which orbitals have the highest probability of finding electrons? How much energy an electron has in that orbital. And that rule is summarized, or that idea is summarized in our first rule of orbital filling, and that is the Aufbau principle. Aufbau principle says orbitals are filled from lowest energy to highest energy. And we use this chart to show us which ones have the lowest energy and which ones have the highest energy. And we said, reading this chart, we look on the y-axis here, and it says increasing energy of electrons in orbitals. So we talked about reading this chart from bottom to top. All right? Good for starters. Okay. So I kind of mentioned before we started the recording, there are 3 rules to orbital filling. 3 rules to determine which orbitals have electrons in them most likely. The first rule is the Aufbau principle. The second rule we introduced to you yesterday was, or Tuesday, was the Pauli exclusion principle. I actually kind of mentioned it a little bit before when we were doing our quantum numbers. What does the Pauli exclusion principle tell us in regards to orbital filling? Each orbital holds a maximum of 2 electrons. Once that orbital contains 2 electrons, it is full, and then we'll move up to the next highest energy. Okay? Good? Apparently we didn't fill this part in. Oh, on the orbital diagram, how do we distinguish between those 2 electrons in that orbital? Up and down arrows, right? We try one arrow pointing up and one arrow pointing down. Say again? What does it say?
It's just a blank one. A. I put off. Oh, yeah.
So, 3 rules. Aufbau principle, lowest energy to highest energy. 2, Pauli exclusion principle, each orbital can only hold 2 electrons. All right, good. So let's review some of our orbital diagrams that we drew on Tuesday. We started off with the easiest orbital diagram, right? That's hydrogen. In order to figure out the orbital diagram for an element, what's the first thing that we need to do? Orbital filling involves which electrons go where. If we're going to place electrons, we need to know how many electrons we need to place, right? So, hydrogen, right? We always start at the lowest energy level. The lowest orbital is 1s, so we draw a line to represent our 1s orbital, and we draw 1 arrow in that orbital to represent the 1 electron that hydrogen has. Is hydrogen's 1 electron always in the 1s orbital? Is hydrogen's 1 electron always in the 1s orbital?
Yes.
Not necessarily, right?
Not necessarily.
So, 2 ways that you can answer that question, right? What are the 2 ways that you can justify that hydrogen's 1 electron is not always in the 1s orbital?
It's in a different orbital.
Okay, well, why? Why? Oh. Okay. What could happen to this 1 electron? It could gain energy, right? We talked about with like the emission spectrum and stuff like that, right? If the electron gains energy, will it be in this 1s orbital? It'll hop up somewhere else, right? What's the other way that we could justify that this electron is not always in the 1s orbital? This is an orbital, right? This is a high probability of finding this electron. But does that necessarily mean that electron will be there? No. So we go with like the most probable option, but keep in mind, right, that electron could be other places, could be in other orbitals, but we go with the most probable option. We say that this electron or these atoms are in ground state, the lowest possible energy. Okay? Good there? All right. Helium looked like this. Okay? How many electrons can the 1s orbital hold? 2. So when we go from hydrogen to helium and 1 electron to 2 electrons, we add that separate electron into this picture, but to distinguish the 2 electrons from each other, we draw 1 arrow up and 1 arrow down. Okay? Edie, what was the next one we did? Lithium. And what was the big change going to lithium? Okay, we added the next orbital. The 1s orbital is full, so we go to the next lowest energy by moving up this chart. 1s is always the lowest energy orbital, but the next one we run into is the 2s orbital. We draw another circle in this case to represent that orbital. We label it 2s. We put that extra electron in it. Is that orbital full? No. Edie, if we had to draw the orbital diagram for beryllium, because you were asking about that before class, right? Okay. So how many electrons does beryllium have? You have a periodic table right in front of you. So 4. So where would the 4th electron go? The down in which orbital? In this 2s orbital, right? So that's why I skipped up to boron, because beryllium is just... Yeah. I mean, that would be mean of me to skip beryllium on International Women's Day, you know. So.
I knew that. No, that's today. I knew that. I actually did.
Yes. Although it's as a woman, I guess I would probably be kind of offended that we get, you know, as a woman you get one day out of the year that's like, hey, Women's Day. Shouldn't it be every day? Like.
You said as a woman on the recording. That's
Said as a woman, if I was a woman.
That was it. As a woman.
It's like all women are
Yeah, basically the other 364 days of the year, I guess. Yeah. So, yeah, it's like, so keep fighting, ladies. It's, you know, so keep working on it. I mean, the fact that society like properly acknowledges you one day out of the year, I suppose, is a step in the right direction. But I mean, you know, it's all over the internet, you know. But we probably should acknowledge you every day. Like that's. I didn't hear that.
Well, that's not good to you.
So. All right. So the next orbital diagram that we drew right at the end of class on Tuesday was the orbital diagram for boron. So going through the procedure, right? First we identify that boron has 5 electrons. Lowest energy orbitals are always filled first, off-bow principle. The 1s orbital got filled first. Once that 1s orbital was filled, we moved up to the next lowest energy. That was the 2s orbital. But then we move up the chart. Yes, we have to move over a column, but the next lowest set of orbitals on this diagram are the 2p orbitals. Because you know about orbitals, if I say an orbital is 2p, what can you tell me about it? Okay, it's double teardrop shape. That's the p orbital side of it, right? What else? A little farther away from the nucleus than the 1s, or in the way the 2p, and that corresponds to what? What about the energy?
Energy level. Amount of electrons.
How much energy it has?
Energy level. Orbital.
The energy of electrons in that orbital are going to be a little bit higher than the energy of the other orbitals. Okay? All right. Here's what happens when we start getting into these types of situations where we have more than one orbital with the same notation. We talked about this on Tuesday. Notice that these three lines representing the 3p orbitals, right? One on the x-axis, one on the y-axis, one on the z-axis. Does either one of them have any more or less energy than the other two? They're all exactly the same. So when it comes up to a situation where we have multiple orbitals with the same energy, we draw them all. How many electrons can we hold in the 2p orbitals? 2 each for a total of what? 6. Combined, these three orbitals can hold 6 electrons. But right now with boron, how many do we have to put there? 1. I put it right here. Is that the right answer? Not necessarily. It is a right answer, but it's not the right answer. What else could we do?
Put it upside down in the last
You can put it upside down in the last one, and that would be exactly just as right as this, where I put it here, or anywhere in between. If we have 1 electron, it really doesn't matter where we put it. There's no advantage to being in the xp orbital, or the yp orbital, or the zp orbital. They're all exactly the same. All right, now let's go on to the next part. Okay. So, Edie, what's the next thing in your carbon? All right. So, first things first, right? What do we have to do first, Edie?
We have to write 6e.
6 electrons, right? Because carbon's atomic number is 6. Lowest energy first. 1s. Edie, you want to use boxes, lines, or circles? You like the lines? Okay. They're the easiest ones to do. Okay. All right. So 1s. Edie, what do you know about that 1s orbital?
2.
It can hold 2 electrons. Okay. So another shorthand way of doing this. Sometimes you'll see this in books as well, but I'm just using like a one-sided arrow. All right. Is this orbital full?
Yes.
Yes. Okay. So we move up the chart. Next orbital we run into is the 2s orbital. Okay. Edie, what do we do next?
We have to put the 2 in the 2s. We can hold 2.
Okay. All right. 4 down, 6 or 4 down, 2 to go. Okay. What's the next set of orbitals that we come across?
2p.
2p. And like we just discussed, how many 2p orbitals are there?
There's 3.
There's 3 of them. So 1, 2, 3. I'm going to label all of them 2p. All right. So here's where we get into the third rule. First rule is off-bow principle. Lowest energy to highest energy. Second rule is Pauli exclusion principle. 2 electrons per orbital. The third rule we call Hund's rule, and I'll tell you about it in just a second. Okay? We saw for boron, we put that 5th electron right there. Throughout this entire process, that's not what I wanted to do. Throughout this entire process, we said there were basically 2 things, 2 ideas that govern this picture, that get us to this picture. What are the 2 ideas that get us to this picture? What determines where orbitals are? What are electrons trying to do? Close to the nucleus as they can. As close to the nucleus as they can, but as far away from other electrons as they can. Okay? So, here we are. We have carbon. We need to place 6 electrons. We have placed 5 of them. The 6th electron can go some places, but can't go one place. What did we say about these 2p orbitals and their energy? They are exactly the same as each other. Is there any advantage to being one of them versus the other two? No. Not really, unless one of them already has an electron in it. Because if one of them already has an electron in it, will the next electron go into that orbital? Why not? It wants to get as far away from the other electrons. So if this orbital already has an electron in it, granted it's not full, but if the 6th electron has a choice, is it going to go in there with the 5th electron? It's not. And so I'm going to draw it here. Is that the only right place for it? There's actually 4 ways that you can draw that 6th electron, right? We can draw it up in the middle p orbital. We can draw it down in the middle p orbital. We can draw it up in the right p orbital or down in the right p orbital. Any one of those would be equally as right as any of the other ones, okay? But you can't draw it in this orbital because that orbital already has 1 electron in it. We refer to that idea as Hund's rule. Hund's rule says electrons will not pair up within orbitals until each orbital contains at least 1 electron. Each orbital in a sublevel. That means like 2 p's.
So when all of the p's have 1. So neon is going to be different, but then sodium.
Hold on. Yeah. Yes, that's where. Yep, that's where it becomes different. Okay. All right. So idea being that electrons will distribute themselves as evenly as they can throughout these orbitals to maintain the lowest energy. Okay. Good. All right. What's the next one on your guys' list? Neon. Let's throw one in there that I haven't given you yet. Okay. So that's not the uranium just yet. All right. Let's go with oxygen. Okay. All right. First things first. Edie, how many electrons does oxygen have?
No, 7. 8. That was right. It's 8.
Okay. Oxygen has 8 electrons. No, I said, yeah, let's do a supplemental one because this is a good one to illustrate this point. Okay. All right. First orbital that gets filled is which one? 1s. How many electrons can that orbital hold? 2. You like the one-sided arrow? So just give it a try. It's fast. So what? Okay. All right. Next orbital to get filled up is what? 2s. Feel free to draw your orbital diagrams however you want to. If you really like doing lines, cool. Keep doing the lines. That's fine. Okay. 4 down, 4 to go. The next level that we come into is what? 2p. All right. Here's where Hund's rule becomes important. Now, I'm going to draw this a specific way, and I will always draw it this way, but on the test, I can't tell whether you drew it this way or whether you didn't draw it this way, so as long as you end up with the right answer, I really don't care how you get there, okay? But by following Hund's rule, here's what should happen, right?
Oh, you want to do 1, 1, 1.
5. Okay. Where does 6 go?
To the right.
To the right.
Uh-huh.
Where does 7 go?
To the right.
Here. All right. Now, all of those orbitals have 1 electron in them. Are they full, though? No. Each of them can hold 2. So where does the 8th electron go? Doesn't matter, right? It can go in any one of those 3, right? I'll put it here just to, kind of be consistent with it, right? But how would, okay, so this is the right answer. Sorry, this is a right answer, okay? Or a right answer.
All right, answer.
But there is a wrong answer.
Any right answer?
There are 3 right answers, but there is 1 wrong answer. What would be the 1 wrong answer for this orbital diagram? Nope.
Well, that would make it wrong, though.
Oh, okay. Sorry. If this one was up, okay. If that one was up, that would be a wrong answer. Sorry. Yeah. All right, Bella. What would be another wrong answer?
If the electron in the last 2p orbital was in the second 2p.
If we had 2, 2, 2, 2, and 0, that's wrong.
Can you move one of the electrons from one s to the last one?
No. Okay. Oh, so like this? Like that? No. Why not? Off-bound principle says we fill orbitals from lowest to highest, right? Is this orbital full? No. So electrons will go there if they have that opportunity. So this is kind of how I explained it this morning, and somebody brought it up. So, okay. If I throw all these balls up in the air, right, and they land, where are they all going to end up? On the floor. I need that for the next part of the demonstration. So, all right. So all of them will end up on the floor because, as far as gravitational potential energy goes, the floor is the lowest that these balls could get to. Okay. I think we kind of talked about this in class. I think we talked about it here, right? You have to fill the entire floor before any one of them would stack up, right? They wouldn't do this naturally, right?
Well, what if we like test it and then just stay there?
Well, will that happen?
Well, I mean, obviously.
So that's the equivalent of filling a 2p orbital before you fill a 1s orbital, right? Does that make sense? Yeah. Well, anyway, go ahead.
I was watching this video, right, where this guy's through a slinky, and if you watch, the bottom of the slinky, like, stays there until the top hits it.
Actually,
Right?
the bottom of the slinky actually moves upward.
Yeah, okay,
So.
like, what? It's crazy.
So,
It's like, okay, so it's falling,
There should be
and
one.
it's
elastic potential energy, the pull of the top part of the spring is actually stronger than the pull of gravity. So it goes here till the rest of the slinky isn't pulling on it anymore, then it'll all fall because of gravity. So, all right, good here.
There should be like stacked golf balls.
Golf balls have flat edges. So, yeah. There's one actually over there.
Explain.
All right, good here. Edie, let's go to sodium. I know, but okay, Edie, when you read sodium, right? 11. Okay. We start with the lowest energy level. The lowest energy level is always what? 1s, right? 1s. How many electrons does 1s hold? 2 electrons. Next lowest energy level is 2s.
Oh man. Oh man, oh man, oh man. Oh, this is easy. I
Huh?
got it. I'm done already.
Is the 2s orbital full?
No, yes.
Yes. Next one we run into is the 3 2p orbitals. 1, 2, 3, 2p, 2p, 2p. Okay? Again, I don't care if you do it this way on the test as long as you get to the right spot. But if we're talking about Hund's rule, right, it would go 5, 6, 7, 8, 9, 10. Okay? All right. Edie,
Yeah.
is the 2p level totally full?
Yes.
Yes.
So then you go 3S.
All right. The next one up on the list is 3s. How many 3s orbitals are there in this picture? Just one, right? The fact that it's a 3s orbital should tell you what about it? It's a sphere, right? It's higher energy level, farther from the nucleus, right? Edie, how many electrons do we have to put in that? Just one. Okay, what? All right, so I believe it says, right, on your notes, noble gas, what did it say? Noble gas notation. Okay. So, here, this is just 11 electrons. It's already starting to get kind of cumbersome. All right? So, we look for ways to shorthand what we've done before. Yes, shorthand the shorthand. If we look at this part of the orbital diagram, how many electrons are we talking about here? 10 electrons. Okay? If we dropped this 3s, this would be the orbital diagram of what? Neon. Okay? Neon has all of the 1s level full, all of the 2s level full, and all of the 2p level full. Okay? If you look on the periodic table, you will see that neon is in the far right-hand column. Okay? We'll learn a little bit later on. We call those the noble gases. Okay? So what we can do to shorthand this notation is the following. See this area that I have highlighted in blue? I can, and we usually use the square brackets to do this, put the elemental symbol for neon in these square brackets, and then we pick it up from there.
And then, big part of this interruption, track is canceled. Girls track is canceled for today. Girls track. Thank you.
Wait. Girls transform?
That's what he said.
Edie, you're done. You're canceled, bro. Edie is canceled. Shut up.
Easy. Easy.
That's because it's national.
That's right. Okay. This is our noble gas configuration orbital diagram. Now, here's something that you can't do. Okay? Here's oxygen. Right? Don't pull this. Okay? This doesn't work. Okay? Nitrogen is not a noble gas. Okay? So, right? That doesn't work. We can only pick it up from the noble gases and then start it from there. Okay? One's on the far right. All right, we will practice some more of these orbital diagrams tomorrow and get you into electron configurations.
Will we even take them tomorrow?
I'm thinking now we might push that take-home quiz back to Monday night. So, yeah.